Hi, welcome to the webinar, Masterclass in SolidCAM 5-axis Part 2. Thank you very much for joining us. We will wait for another 2 to 3 minutes for people to join in, and then we will start at exactly 5:33 p.m. India time. Thank you very much for your patience. Hi, good evening from India. Welcome everyone to this webinar, Masterclass in SolidCAM Sim 5X Part 2. In Part 1, we have seen the generic milling. I'm going to continue a portion of generic milling today because I'd missed certain aspects of generic milling last time because of time constraint, because the fact that SolidCAM's 5-axis is pretty vast. Most of the things cannot be just covered in 2 or 3 classes, but we are trying to fit in as many features, as many things as possible. So today I'm going to go and delve a bit more deeper into the other aspects of the generic 5-axis milling, which we missed last time. So today, again, we are going to see the following 3 things: the 5-axis offering that we have been seeing since part 1. We will see live paths, and then I'll summarize at the end whatever we did today. So just as a summary of what we have inside SolidCAM, we have generic 4 and 5-axis milling. We have seen some portions of it. We have multi-axis milling, multi-blade milling, port machining, rotary machining, edge breaking, edge trimming, and auto 3+2 roughing. Out of which we have seen the generic 4 and 5 milling and auto 3+2 roughing last time. We're just going to delve more deeper into the generic 4 and 5-axis milling. So the other things, we are going to leave it to our part 3. Today, I'm going to talk and I'm going to show you more about barrel tools or the circle end mills. Basically, the circle end mills are getting more and more popular. More and more manufacturers are coming up with this new product line where they claim up to 90% of reduction in machining time when using circle end mills. And as far as SolidCAM goes, we introduced circle end mills way back in 2019 version of SolidCAM. And since then, we have been improving it over the past couple of versions. We support barrel shape, oval form, taper form, and lens form tools. So we support almost the most common form of circle end mills. Of course, there is something called as a double barrel. We should start supporting it pretty soon inside SolidCAM. So right now, we have the most common four shapes in SolidCAM. Apart from the generic machining in SolidCAM, the 5-axis one, we have some very interesting strategies that form part of our generic bundle. And one of them is the rotary 4-axis finishing. Rotary 4-axis finishing is a very powerful module. It's designed for finishing 4-axis parts that are rotating around the particular axis, just finishing. It can be used to mill cylindrical parts like bottle molds, cores, electrodes, jewelry rings, woodworking parts, etc. Tool paths are directly calculated on 3D geometry and not wrapped around. So it's directly, the calculation happens on the 3D geometry. There are two types of strategies available. You can go along the profile or around the profile. And in both the strategies, you can, or SolidCAM allows the tool axis to be shifted from the center line by any value that the user defines inside the parameters. So the tool need not be exactly at the center. You can shift the tool away from the center so that you don't use the tip of the tool, but you use the side of the tool to machine. I'm going to show you an example in this. Apart from that, we have Warf Machining, which is a very robust engine for machining parts using the flank of the tool. Absolutely minimum inputs. We are going to see a part today in it. Clean results because unlike the generic 4 and 5 axis system of SolidCAM, Swarf uses an intermediary mesh it generates to work on it. So naturally, the results are going to be clean. In spite of giving it bad surfaces, it will still generate a clean result. The tilt control is automatic inside Swarf. And almost every user that I've seen will need swarfing or will need machining using the flank in some form or the other, or in some part or the other. So it's a module that is built into our generic bundle. And the output is in both 3-axis swarfing. I don't know basically where we would use it, but we do have an output that can generate a simple 3-axis output. We can have 4-axis output and of course the 5-axis output. Almost every tool is supported in Swarf machining. And applications used are basically impellers, frame components, and production parts. So you can machine almost any surface now with Swarf. And then we have a very interesting functionality for die and mold makers where we can convert an existing 3-axis toolpath, whether it is a rest roughing toolpath or a finishing toolpath, you can actually convert it to 5-axis straight away without any user intervention, without defining anything major, putting geometries or trying to put in several parameters. Nothing of that is needed. It's just a function called as auto tilt, and we generate a simple 5-axis toolpath out of a 3-axis rest roughing or a finishing toolpath. Both HSM as well as turbo HSM toolpaths are supported inside this particular strategy. So the advantage of the strategy is that the user can machine really deep paths using very short tools, because once you tilt it, you can really approach the deep areas of a die mold part. We're going to see a part today also. I'm not going to explain to you how it works. The process is completely automated and absolutely minimum user intervention is needed into the entire tool path. Part of the generic bundle, we have something called as a multi-access drilling. This particular operation inside SolidCAM's 5-axis bundle takes advantage of two things. One, it takes advantage of SolidCAM's hold recognition process, And second, it takes advantage of SolidCAM's 5-axis tool-axis control. So it combines both the hole recognition process and the tool-axis control process to generate a 5-axis drilling program. All advanced linking, tilting, and collision avoidance, whichever that are used in our generic 5-axis, are available in multi-axis drilling. The drill depths are automatically determined because it is using the hole recognition process wherein SolidCAM understands what's the depth of each hole, and the depth of each hole is then assigned to to the tool path. So the drill depths need not be defined by the user. That gets picked up automatically by the software, but SolidCAM does allow you a facility where you can alter the depth of each of this hole. For example, you're just doing a centering and you don't want the centering tool to go all the way down up to the hole depth. So you can say all these groups only 1 millimeter from the surface. So you can alter the depth of either one hole or group of holes. Then we have another machining concept called as contour 5-axis machining, which is used for machining the edges of a part. In this case, no surface input is needed. In fact, there is no way you can put in a surface input. It only needs edges and it needs tilt lines or orientation lines. With help of these two geometries, it can machine edge on a particular part. Now, there are many applications. This is a pretty one of the oldest functionalities inside SolidCAM's generic 5-axis. And earlier, before the advent of edge breaking and other technologies, this particular technology was used for doing chamfering and also trimming of vacuum form parts. So this still continues to be inside the generic functionality, supports different cutters. Okay, there is no limitation on the type of cutters that can be defined with this. It supports almost everything that is there inside SolidCAM. And finally, we introduced a year back a machining process called as geodesic machining. Basically, geodesic means if I let's take an example. You have a tank of water, and you have a wire of a particular shape, and you drop the wire perpendicular to the water. The ripples that get generated are basically having equidistant from each other. They are equidistant from each other. It doesn't matter the shape of the tank, but the ripples are always constant. They have a constant distance between them. The same principle is applied inside SolidCAM's geodesic machining, wherein the global distance or the distance between two passes or two slices, it does not uh, get restricted to a fixed direction. Generally, in 3-axis, you always look from the Z direction and the toolpath is generated. So when you have a vertical wall, you actually get much bigger spacing between them, between the passes. In 5-axis, it will always look perpendicular to the tool axis. Whatever tool axis you have used, it will always look perpendicular to the tool axis and generate the pattern. But in geodesic, it doesn't use any fixed direction as a reference, but it always looks normal to the surface to generate a distance between the two patterns. So finally, if you have set 1 millimeter as your uh, step between two slices or two patterns or two passes, it will always ensure that that 1 millimeter is maintained irrespective of where it is cutting and what is the kind of surface that it is encountering. I'm going to show you a very simple example in which I can show you that it doesn't matter how the tool looks like or the how tool looks into the part. The distance will always be constant. The best part of geodesic is it works both on the mesh data as well as surface data, so it can handle both of them. A portion of this engine is already available inside our generic 4 and 5-axis machining. If you go into the toolpath parameters, you have the option of approximate and exact. When we select the exact option triggers the geodesic engine from in the back end, and the calculation completely happens using the geodesic engine. Okay, but since the machining works only on, or our generic works only on surface, so we only take the surface groups as an input when we use the exact one. But in geodesic, it allows you to do both mesh as well as surface. Right. Uh, let's uh, let's go into a part. So I told you that we are going to start with the circle end mills. So I'm going to open a part. Let's start with the most simplest form so that you understand what it looks like. So I'm going to open the turbine blade that we saw in the first part, and we are going to run the machining. So if I go into my toolkit or the support of the tools, you can see that we support the barrel shape, we support oval form, we support the lens form, and we support the taper barrel. So we support the four most common type of tools that are used in the industry today. Of course, like I said, there is a double barrel, but it is very rare that people use double barrel these days. But we should have the support of it pretty soon. So I have a oval form tool with diameter 12. So this is how my tool looks like. I've already defined. If you look at the large radius, the large radius is 80 millimeters. So we are taking the advantage of 160 millimeter ball nose cutter in cutting this particular part without having to define such a huge cutter. So the advantage is that you get uh, bigger side steps. You can take bigger side step without compromising on the scallop height. So where on such parts you would take 0.2 to 0.3 to maintain a scallop of, let's say, 1 or 2 microns, you can take similarly about 1 to 1.5 millimeter step and still maintain the same scallop that you would maintain with a smaller ball nose end mill. So we are going to use this particular tool. I'm going to define a new process in Sim5X. I'm going to use morph between two adjacent surface, and I already have some of my faces out here. So this is the faces that I'm going to select. So I have my library of faces that are already stored. Now, this is something very old to SolidCAM. We create these groups and they are stored inside the file. So whenever we would like to use something, we can always reuse geometries. So I have faces 1. I'm going to select that. And my start edge is going to be the surface on top. And I think even I have that, yes. So that's the start edge. And the end edge here is this one. These are the faces that I'm going to use. Okay. So the pattern will be morphed between these two surfaces. All right. So I'm going to start and end at exact surface edges. So but of course, there is a small margin to overcome the surface inaccuracies. This generally is needed for people who import data from a different software. If the part is being generated or developed inside SolidWorks, generally you don't need to provide any margins, okay, because it's pretty accurate. But when you're importing an IGES file or a file through another CAD system, in that case, when you import a lot of inaccuracies of the surface edge that creeps in, and to overcome those surface accuracies, we provide some kind of a margin so that we don't have any issues with the toolpath slice. Right, the tool we are going to use here is the oval form tool, diameter 12. Okay, and nothing to do with the levels. Toolpath parameters, I'm going to give a step down of over 1.3 millimeters. This generally will give me a scallop anywhere between 2 to 4 microns. Okay. And in the sorting, it's going to be a spiral toolpath. Now, the most important thing in using barrel tools is the tool axis control. The tool axis control here is slightly different than the ball nose or a bull nose tool. So we will use the contact point method in defining the tool axis control. We're not going to be defining any angle or anything like that, but purely based on the contact point. And the contact point can be defined by two methods. Okay, let's go into my tool. Just going to because I would like to explain to you more in detail about how it works. Okay, so I'm going to zoom here and I'm going to capture a view. Okay, let me go to my graphic tablet and we'll make a few drawings here. Okay, so you have this one here. This is the large radius. And then you have got a small radius out here. This is a small radius, okay? So the large radius in this case here is 80 millimeters, and the small radius here is the 2 millimeters. So this is R80 and this is R2. So when I go into my tool axis control here, when I go into my tool axis control, I have got two possibilities, one by height and one is by line parameter, okay? So when I go into my height, you can see that there is nothing, because what it basically means that this will be considered as 100%, and this one here down will be considered as 0%. So if I say put this value here, if I put this value here at 50%, it means I am asking SolidCAM to maintain the contact point always at this particular point here, at which is 50% of the flute length. But we have got another method which is called as the line parameter. And in the line parameter, we have got again two options. So what is the line parameter? In the line parameter, we take into account this entire length of the cutting area and not just the height of the cutting length, or just the height of the cutting area. We take the length of the profile. Now in the length of the profile, like I told you, there are two methods. One, you can take the complete line, or you could just say the barrel section, okay? You can say the entire profile or just the barrel section. Most of the times we use only the barrel section. So we take this as 100, and here this portion becomes 0 for us. So we can then place the contact point anywhere between this area. So I can say 0 will be exactly at this point, 50% will slightly move up somewhere here. Okay, this is 50, and then you have 100%. So you have got the option to place it along the barrel, and then you can also dynamically adjust this so that you avoid giving any collision checks in to the profile. So you can say go from 50 to 20, which means it will start, my first contact point on the first cut will be here, and my last contact point on my last cut will be somewhere here. So it will keep altering the contact point between this area here. Okay, so you can say that, let's say at 50% it was getting 70 degrees as the tilt, maybe at 20 it will get it at 45 degrees. So it will keep altering the tilt angle between this. So we are going to use this method. I'll say 50 to 20. I won't do anything with the gauge check. I'll just save this toolpath and let's calculate this toolpath. It should be a pretty quick calculation. Done. Just ignore it for a moment here, and you can see how this simulation looks like. So if I run the simulation, let me do the first few cuts, and then let's zoom in here. You can see which portion of the tool is in contact with the surface. You have got somewhere the contact point to be around this point, which is in touch with the surface. But if you look at the tool path, it's already gone below, okay? So people generally have a feeling that, why did my toolpath start from bottom and why did it not start from top? This is basically the locus of the tip. How the tip is going to move, the tool tip, it is showing that, the toolpath is showing that. But actually, we should be more concerned on what should be what is my contact point. Okay, the contact point is somewhere up, the tip is down here. Okay, so this is how it's actually going to cut the part. Now, to fix This issue at the bottom, it's pretty simple. I'll edit this toolpath. I'm going to go into gouge check and enable the gouge check. And I'll say trim and relink with the check surface, which is the check surface here. Let's go, let's find out. Not that one, not that one, not that one either. I think it's faces 3. Yeah. So faces 3, these are the faces that I'm going to like to check the toolpath. And I'm using the trim and relink, but in trim and relink, I will say trim between the first and last collision. Keep a gap of 1 millimeter from the check surface and just check for the tool shaft and the tool tip. I'll just calculate the tool path. And it should be done. So we fixed the problem. We might change a little bit more of the margins maybe here, the end margin. And of course, a bit of the gouge check if it's coming too close to the profile. Oh, we still have. Let's check the other toolpath that I have here. Let me unsuppress it. And let's calculate this toolpath. It's the same. Only thing the change here is the contact point. I think I started from 40% and I went to 20%. Probably that's the whole thing. You can see how it works. And if you look at the simulation of the machine, this is how it would look like. It's pretty clean. And instead of using a ball nose end mill or even a bull nose end mill, you can end up using a oval form tool. This is how it will cut. Pretty clean, smooth motions on the machine. Right. Let's go ahead. We saw a closed turbine now, sorry, the open turbine, and I'm going to show you the open turbine, closed turbine rather. I already have the toolpath. So in this particular example of the turbine blade, I have actually used a different circle end mill. Okay, this is also pretty commonly used nowadays for these kind of components. So for machining the aerofoil area, there are 3 possibilities here. One, we could use a simple ball nose tool, okay, where you can put the, if I just simulate this, you can see the contact point. It's using the tip as the contact point, okay, or just the slide side because I've tilted the tool. But still, the diameter will not be big, okay. It still will be a very small diameter, and you will have to give a very small step over. The other possibility is to use a bullnose tool. And here, again, we can use the front of the tool to machine it. But again, here we are restricted to the diameter. We cannot use a bigger diameter because of the part size itself. Okay. The other method of reducing the time would be to use a tool called as a lens form tool. Okay. So that's what we have here. I'm going to use a lens form tool. So the tool here I'm using is a lens form tool. So if you look at the lens here, or the tool form itself, this is how it looks like. I'll zoom it. It does not have any radius on the side, okay? There's no radius on the side. There is a small radius here, and then there is a large radius here. What is that radius? That radius is the large convex tip radius is 20 millimeters, R20. So it's like using a 40 diameter ball nose tool to machine the part. So you can imagine the kind of step over that you would give to a 40 diameter ball nose tool, you can give the same to this diameter 10 R1 with convex tip radius as R20. The same step over you can provide to this particular tool. So when I go back into my tool axis control, because everything else remains same, the only thing is the tool axis control, like only that will change. Again, here I'm using the contact point, but instead of barrel section here, when I switch to a lens form tool, I get the full profile or the convex tip portion itself, only that R20 portion. So it's asking me, where do you want to place your contact point? So I'm asking SolidCAM to place it at 50% on the contact on the convex tip profile. And this is how the toolpath would look like. So if I look at the contact is somewhere here. Okay. Now you can have two types of contact because this is like almost like a spear. You can have contact here on this side of the tool, or you could have contact on this side of the tool. So it depends on which side is the tool tilting. You can change that contact point by simply clicking this button of using the negative tilt. So if it's tilting on the positive side, selecting the negative tilt will push the tool and tilt on the other side. So if I run the machine simulation, this is sorry, don't see, the tool. I'm so sorry. Maybe I picked the wrong machine. Yeah. Anyway, so let's run the simulation here in the Solid Verify. I mean the okay. And look at the that's crazy. We have a toolpath here. So this is how the toolpath gets generated. I can give a bigger step over. I would have normally given about 0.3 millimeters here if I was using a 16 diameter ball nose tool, or even a 16 corner radius 2 or 3 millimeters bull nose. I would have given about 0.3, but here I've gone up to 1.2 millimeters step over. So straight away my machining time comes down dramatically. Right. Uh, Further delving more into the circle end mills, because I showed you two paths. Now I would like to show you another part which is a very good candidate for such type of tools. Okay, so I'm going to show you a blisk. A blisk is also a very ideal candidate to machine using the generic 5-axis. Okay, so here I have done everything using the generic 5-axis, including the roughing, the finishing of the blade using the oval form tool, finishing the bottom, and whatever area remains, and of course the floor can be done completely using the generic 5-axis. So I have got the roughing here, which is basically using the same method that I showed you in the impeller last time, but the tool here this time I'm using is a bull nose 12 corner radius 2, and that's it. We'll just calculate the tool path. It calculates the first slice and then runs the roughing of all the slices in between, and in the end just connects and does the transformation for the number of blades or area we have. Okay, that's done. Took about 35 seconds to calculate. Okay, So this is how the roughing would look like. I've simply used a bullnose tool here and machined this entire part here. So first roughing, and then for finishing, I've used two methods here. Okay, the first one uses the blisk, not blisk. I'm sorry, we are machining a blisk. The first one uses an oval form tool. So let me check this tool path, the parameters basically. So I'm using a morph between two boundary curves. And if I look at the surfaces that I'm machining, these are the surfaces that I'm machining. And the upper curve is that pink colored stuff. And then we have the lower or the end edge curve, which is the bottom curve. So I'm driving the toolpath pattern between these two, and that's the tool. So we are using an oval form tool here, and which is basically a 10 with, let's check the parameters. It's 10, and the large radius is 85 millimeters. The small radius is 2 millimeters. So that's an oval form tool we have. And in the tool axis control, I am tilting it, my first contact point, okay? My first contact point when it machines this particular edge is at 50% of the barrel section. And the last one, which is at the final end, is when the tool will have a contact point at 20% of the barrel section. That's all that is needed. And in the collision check, I have asked the tool to tilt automatically against the drive surface so that we don't touch the arbor or the holder into the part. And then for the bottom surface, because it should stop, it should not collide against my floor, I'm trimming the tool path wherever there are collisions. So let's calculate this tool path. The biggest part or the most complex part in this is always the collision check, because it needs to check the tool's shaft. It needs to check the cutting portion. Also, it needs to check the holder. But here I've got two groups. First, it needs to check with the holder, with the drive surfaces, and then it needs to check with the cutting area to the bottom floor surfaces. So it's a pretty complex operation. Another very important tip here, the priority or the order of gouge check matters a lot in SolidCAM. If you get the order wrong, you can get your results also wrong. Okay, so it's very important that when you have two collision checks, one is tilt and the other one is retract, you get the tilt first and apply the retract as the second one. If it's only retract, then it doesn't matter. But if it's tilt, the tilt always gets the higher priority. Right, so we have this toolpath here, very nicely done. And let's run this machine simulation on this part. Here we have the, I think it's the new generation Haas 1500 SS Duo. It's got both 5-axis and 3-axis tables. Yeah, it's the Haas 1500 SS Duo. Okay, that's done. I'll just switch off the machine housing for a moment so that we see what's there inside. So this machine has got two tables. One is a 3-axis table, and the other one is a 5-axis setup. Both are in the same machine. So we're going to run the simulation on this. That's pretty fast. Okay, we can slow it down further. Switch off the toolpath. And that's how the tool is going to move on the machine. This is basically the oval form tool. So Where I would end up using, let's say, 0.2, 0.3 millimeter step down, I'm actually going between 1 to 1.5 millimeter. So you can imagine straight away we have got a difference of 60 to 70% time between both of them, because the feed rates are almost similar to these tools, the kind of feed rates that we use. As you can see, as it's going down, it's actually getting more and more complex because the holder is coming into play. So we have applied the collision check, and because of that, the collision check, the tools or the table is tilting more than what it would need if only the tool was checked for collision. Okay, so the advantage here is that you can still use short tools, because most of the barrel tools are always short tools. You won't find long series in barrel tools, at least not right now. I have not seen it with any manufacturer. They're all short. You can use the short series and really go deep. But the disadvantage when you're going in such parts is that the tool cannot reach all the way down. So there will be some portion of the material that still will be left out, which will be unmachined. Okay. So for that, what we have done here is I have done the finishing of that short portion here, whatever area that remains. I'm doing it with a taper ball nose. Okay. So here I don't have a choice. I have to use a taper ball nose to finish all the way down. And here you can see that I'm using a much shorter depth of cut because it's a ball nose. And how the tool looks like, it's basically, this is how the tool looks like. We're using a taper ball nose of diameter, I think it's 12 with tip radius 3 millimeters. Okay, so let's hit the calculate button. Simple. The tool axis control is tilted through curve. And if I show the curve, this is the tilt curve that I'm using. Like you saw in the impeller, we have just offsetted the upper surface, created a ruled surface around the edge, and this curve was generated. So let's run the calculation. This also should be pretty quick because the number of passes are very small. Again, the only time that it takes is when you apply collision checks. The other calculation is pretty quick always. Okay, so I have got, you can see there are very few passes here. Let's switch off the tool. So this much portion is actually unmachined with the barrel tool. So this area has to be machined using a bullnose or ball nose tool, not bullnose. So again, this is how the machine would look like, or the machining would look like. Again, you can see very clearly we have used the collision check. So as it comes closer and closer to the part, the holder comes close to the part, it will start tilting itself. Okay, so we have precariously close, but don't worry about it. As it comes close, it will tilt, finish, and then move to the next blade. Okay, so collision checks are taken care. Finally, what remains in this particular blisk is machining the bottom. The bottom is the copy of the first roughing operation itself, but instead of using a bull nose, I've used a taper ball nose. I'll just calculate because it's the same as the roughing. Only thing, we don't have multiple passes here. We just have a single pass. And that's how the floor looks like. So with generic, actually, you can machine it using anything. I mean, you can machine any part. Oops. You can machine with any part. You can see the how close the tool is with a part, but not, there is no collision. How close the holder is, no collision. Okay, these are taken care by SolidCAM. So a blisk is also a very good candidate for circle end mills. What is the other part or other kind of parts that one could use with circle end mills? Okay, we're going to use another one. That's probably the last part I'm going to show you with circle end mills. And this time it's a complex aeroframe structure. Okay, so I have got an airframe structure that I've mounted on two vices. Of course, the stock is being held on two vices, and we are machining this. The machine that I'm using here is a DMU 125P with Heidenine ITNC 426. So I'm going to focus myself on some areas of this. For example, let me edit this toolpath. Maybe this one, yeah. So I'm going to edit this toolpath. And I'm using parallel to curve. And the surfaces that I have here, if I show the surfaces, I've picked this area as my surface. And we are going to machine that using a oval form tool. Or in this case, I'm not using an oval form. I'm using what we call as a taper form tool, which has a diameter of 10, corner radius 2. Now look at the taper form tool. The taper form tool gives you a big advantage, jump. It has got a radius, the large radius of 250 millimeters. So it's like using diameter 500 tool. The advantages of using diameter 500 tool on the surface can be achieved by using this tool. So you can actually go 1.5 to 1.7 millimeters easily, still generate about 1 or 2 microns scallop. That's the best part of using these tools. So I have this tool, and at the tool axis, here I'm using a constant contact of at 40% of the barrel section. This is it. And in the collision check, I'm just retracting against the check surface. So whatever are these fillet areas, I don't want the tool to touch the fillet areas. They should just retract along the tool axis. What about the link? Okay, what I'm going to do here is I'm going to say, don't use anything, and go to the clearance area. We're going to play a little bit here, a couple of minutes, I would say. And I'm going to run the calculation. So what is the first thing that you see here is we have got retracts. Now, if you look at a lot of videos that are there on YouTube about how the machining happens with the circle end mill or with the barrel tools, you'll see that there is a cut. There's no retract. The tool comes back almost on the same level and machines the next layer. Okay, that can be easily achieved in SolidCAM's generic 5-axis. It's basically nothing but simple link. So what we are going to do here is I'm going to go to the link, and the link between slices, that means the passes here, is going to be connected directly. Okay, let's calculate and let's look at how the connection looks like. So you can see that they are connected directly, but this can be catastrophic here, because you can see that sometimes because of the curvature of the part, the connection can actually cut through the surface itself, which is dangerous. So instead of going straight away directly, I'm going to apply some link to it. I'm going to say use lead in and lead out. What is the method of lead in and lead out that I'm using? I'm using an orthogonal line. That means I'm going to get a normal line every time at the end of the toolpath or the start of the toolpath, which will be approximately 10 millimeters, and it will not be a straight, or it will not be parallel to the toolpath. There will be a slight tilt of 1 millimeter, so that when it comes to the end at the bottom, it doesn't touch any of these surfaces. It's always above safe. So I'm going to use this method here, and let's run the calculation. Perfect. So you can see what it did. It generated a 10 millimeter line here, connected, back again. It machines, retracts, goes straight, connects back. This distance you can control based on the curvature of this part. I have just given 10 millimeters. You can even give 3-4 millimeters also, depending on how the curvature is. So let's run the simulation on the machine. So again, here I have the DMU 125P door block. Let's switch off the housing, and I have the tool, the machine, the spindle, everything mounted, and we can start the simulation. Oops, that's pretty fast. You can see the retraction is happening pretty quickly, so we'll stop that. I would like to go back, and instead of NC mode, I'll go into the time mode, and let me run the simulation. So now it's moving on the time mode because it's using the same feed rate to machine the or to retract back. If the feed rate was higher, you would see that this would have come back quicker. So let's make that quick change. I'll edit this toolpath. Go into the link, and I'll say the feed rate for this link should be 10,000. Let's calculate. Going to go to simulation again with the machine simulation. Okay, zoom into that area. Time mode. Let's start. You can see now it's much more quicker. When it's cutting, it is cutting at the cutting feed rate. I think it was 1,000 here. But when it comes back, it will come back at the 10,000 feed rate. Because I've used the time mode, it'll be much quicker. Okay, so that's how it's going to machine. You will always see the large radius of R250 that is in contact. So whatever 1.5 millimeter I've used here will help me generate that scallop of 1 or 2 microns on this particular surface. So you can actually use generic to machine any kind of part using circle end mills. We have absolutely no restriction or no you can say uh, you it won't happen that you can't machine a certain part with SolidCAM using the generic and using the circle end mills. You can use any kind of tools, any of those 4 tools that we have specified. All of them can be used to machine the part easily. Another thing that you would have noticed is that when this particular area is machined, the fillets are machined in a different way. Okay, that also can be done very easily inside SolidCAM. So what I've done here is not that one here. I've done what we call as a parallel to curve functionality. In this case, I have got, these are my drive surfaces, or these are the surfaces that I need to machine all this fillet area, because everything else will be done with the barrel tool. And these ones, you can use the tip of the barrel tool, or you could use a taper ball nose. You will end up getting the same time and same result. Okay. And the curve that I'm using is this entire area. This entire area is the area that it's going to follow, the curves that it's going to follow. And the tool that I'm using here is a taper ball nose tool with 12 corner radius 2.5 R. Okay. And the tool axis control here is tilted through curve. So which is the curve here? I've just created a simple curve. Now, how did I do this curve? I can explain to you in a minute. Sorry. Let's cancel. Not that, sorry. So what I simply do is I'll create a reference geometry, a plane parallel to this, and let's go up. I'll go beyond the one that I just used it. So I'm going to use the plane there at 190 millimeters and create a sketch. Now, the best part of SolidCAM comes here, that you are always in the CAD mode. You don't go out, close something, clean up that area, go into a completely different environment, and then do the CAD work, come back again. No, you're always in the CAD mode. So I'll convert these edges here. So I've got these edges, 3 edges or 4 edges I have. So I've converted this edges, and I will offset them. So I'll create an offset of 20 millimeters for this one, 20 for this one, and maybe 20 for this one. Okay, so I'll select OK. In the meanwhile, these geometries that were created as an offset, I would like to just create it as construction geometry. And then I'll apply a fillet of, let's say, 25 millimeter between this geometry and this geometry. This geometry and this geometry, of course, will not happen. So what I will do is I'll delete this and just drag this fellow. Can I? No. So I'll create a new line altogether from here, follow that. And this small one, oops, that's not the one. Let's delete this. This one will be construction again. And we create a small, another curve that will follow that. Yeah. So fillet 25 between this and this and this and this. Done. So I have the curve. So I will go back. I'll go to the operation here. I'll copy this operation, paste it, because I would like to show you the advantages of working inside the CAD engine. Let's edit this geometry very quickly. This is the last toolpath inside it. And the tilt curve here I'm going to use is not 53, but this one, this large one. Yeah. And use the closest point, and I'll run the calculation. I don't know if you observed when I started calculating this, because I'm using the exact method, it said calculating geodesic toolpath. So it's using the geodesic engine at the background. You can see, first of all, what has happened is that curve is not good enough for me. There are collisions, so it is trying to pull the toolpath up. Why? Because if I go to the top view, and if I look where this curve is, you can see where this curve is. This is not good enough for me. So of course, it's not going to work. So the best part here is I can edit this toolpath or edit this curve. I can make another curve somewhere here, okay, and provide a relation between this and this. Say this is parallel, okay, and then put another fillet between. Of course, I'll break the relation. That's a different thing. Okay, and this particular toolpath, or this particular curve that was there. Sorry, not the fillet. This particular curve that was there will go into construction. So I changed my curve here. Okay, I changed my curve. So in most of the softwares that do 5-axis, you need to reselect this, not SolidCAM. I simply will go to Control 57 and I'll ask for synchronization check. You can see that it has found that there is a difference between what was provided earlier and what is available now. So there is a difference. You can see that it's showing that it is missing certain areas. So I'm going to right click on this and I'll say, please synchronize with the new one. That's much bigger. Okay, it's unable to synchronize. So I can always go back to edit only this particular curve and we'll edit this chain. Yes. Okay, there's a gap. So I'm going to pick this. Let's delete this chain straight away. And I will pick this one, change the direction, and this one. Okay, that's done. Simply, I need to calculate it, nothing else. Okay, that's much better now. No more retractions that are happening. There are only jumps. That's okay because there are 2 regions that it has detected. Now, if I go into the simulation of the machine, that's how it's going to look like. Okay, so that's my tool material again. Let's run the simulation. So it's jumping between two. You can see that there are collisions because I have not provided any collision check to it. And one of the reasons why it is colliding is here. The element of the machine is colliding against the part. It's not the tool or any other geometry. The element of the machine itself is colliding. So one of the remedies here is to increase the holder length in such a way that we get completely different tool path. The other remedy here is to change the tilt control itself. So I have got the earlier one, which I have defined, the tool path. I have got the curve on a completely different plane. And you can see that, sorry, I don't have any collisions as such. There's no more collision because I've used completely different plane here. Okay, right. So that was about circle end mills and their application. Let's move ahead. The next item on our menu is the drilling. I see that there are already questions about drilling, so we're coming to it. So I'm going to open part here for drilling. So multi-access drilling is good when you have got holes that you need to drill from different directions. And there are hundreds and hundreds of holes. And there, making a plane and making the direction, it's time consuming. Instead of that, you can use the hole recognition technology of SolidCAM, couple it with the 5-axis tool-axis control, and you get a 5-axis drilling operation. So what I have here is I have a Hermle C32U on which I'm going to show this particular part. So I'll go into the operation, I'll edit it, and I'll go into the geometry and I'll say, I would like to make a new geometry of the part. So I have got the target, so I can define a target or I can define another target here. I already have defined the target that I would like to machine. You can apply filters. Now, what are the filters? The filters are different filters in which the holes will be picked up by SolidCAM. So what the first type of filter is a hole type. You can filter out by holes that are either through or blind. You can pick either of them or both of them. You can say that I just want to have blind holes. It will only pick those holes that are blind. It will ignore the through holes. Or you could say I just want through holes, ignore the blind. It will do that. Or you can have show me both the holes. The other one is that you can ask for a particular hole diameter only. So you would like to drill 6 diameter drills only. You want to use a 6 diameter drill on the entire part, and you'd like to find out where the 6 diameter holes are. You can specify this diameter. You can say 6 diameter 6 to diameter 6. Okay. Or you could say, show me holes from diameter 3 to diameter 6. Okay. You can have even a range, right? Or you could say, show me by hole height from a particular height from 0 to minus 25. Show me all the holes. So it will show you all the holes within that range. Or most of the aerospace components are already color coded. If the part is coming from CATIA, and if you are importing using a CATIA converter available with SolidWorks, then you'll see that the holes are colored. Okay, so you can specify which color you need to pick. For example, you can pick from the model, let's say the green colored holes. So I can pick this. You can see that it found the RGB code for that particular color, and simply I say define. So it will pick only the green colored holes on this entire part. Okay, so that's another one. But here I would like it to find all the holes that are available, and then we will pick up from there. So I'm going to say find holes. So it immediately gave me about I don't know, there are more than different groups here. Shapes. First of all, we have It segregated it into shapes. So we have got different shapes, and each shape has a group of holes. So for example, I click on shape 1. I right click on that and I'll say show hole. So it's showing me the holes which look like this, which have a chamfer on the top. There is a counter bore, and then there is a through hole. All these holes are being shown currently. Then I have group or shape number 2. Right click on it and I'll say show hole. It just has a chamfer and a through hole. That's it. Then we have shape 3, which has got a counter bore, no chamfer, and a through hole. Then we have shape 4, which is just a simple through hole, no chamfer at all, and so on. Shape 5, which is chamfer, counterbore, chamfer, counterbore, chamfer, and then through hole. Then shape 6, and so on. So it's picked all the holes. Okay, fair enough. So I have got all the holes here. I'll accept this and select the tool. So I have a tool here. It's diameter 6. So I'm going to use diameter 6 here. Let me use the previous one. Yeah. So I've got a tool which is diameter 6. Levels, you can see that it's automatic, and I don't need to define anything here. Even the depth is automatic, but if you're doing a centering, you can always edit the depth, and you can pick all the groups, and you can apply a particular depth to all of them and say 2 millimeters from the surface, wherever that surface is, you can define the depth. We come to the technology. Depending on the post processor you're using of the machine, you will have the cycle type. For example, here I'm using Heidenhain, so I have cycle 200, 201, 202, 203, and pecking, which is 205, tapping 207, boring 208, and so on. So I'm using drilling 200, which is basically the equivalent of G81 in Fanuc. Now, the question many people ask me, or some of the people have asked me, is when you use a cycle, you have problems of the depth. I know this problem, but this problem is basically related with your post processor. So you need to get in touch with your person who made this post processor and get it corrected. Basically, my recommendation here is not to use any cycle here. It just, if I don't use any cycle, your G81 will be broken into linear moves. So it will mimic a drilling as if it's doing a drilling, but in linear moves, okay? And then, of course, we have got the sorting here. So I can look at how the holes are being sorted out, how it's machining them. So fairly, this looks to be okay to me because I'm going with the shortest distance. From each hole, it will find the shortest distance to the next hole, and it will capture that and sort the operations in that way. Okay, say done. Go to the tool axis control. I have got the output as 4-axis or 5-axis. I'm going to use 5-axis. The only thing here I've done is I have used collision control. Why? Because I don't want the holder, because if the hole is too deep and my drill is small, I don't want it to go all the way into the part. So I have asked the collision check to retract the tool whenever it is colliding against these surfaces that I've picked up. All these surfaces, it will check for collision. Okay, perfect. That's all. I hit the save and calculate button and I get the tool path. So if I run the simulation, okay, we're on this side. So it will machine all your holes without you having to define any plane or anything like that. Simple mimicking of linear motions. Right. Now the best part with 2021 of SolidCAM was the Simco integration. Anybody who has bought SolidCAM's subscription in 2021, I think after May 2021, is automatically entitled to get the Simco integration into SolidCAM. So they get a Simco professional license, a legal license, along with SolidCAM, and that's completely integrated. So if I generate the G code here, yeah, let's just generate the G code. You can see it'll open Simco in the background, open the G code. I'll go into my backplot setup, and in the backplot setup, we have got several machines. So I'm using the Hermle C42 here with Heidenhain ITNC 530. They don't have 32 here, so I'm using 42. But the height and height control is the same. It's 530. Say OK, and now I'll go into the backplot window. You can see that the part along with the tool path is already displayed. So you have got the G code, and you can actually run the simulation of this inside Simco. You can really check your G codes even before you take it to the machine. That's the best part about having an integration with Simco. Right. This is something that people are able if they have signed the subscription with 2021. So please get in touch with seller or your direct office for further information. Okay, let's move ahead. Part of the generic is also what we call as the conversion. So I have got a part here. Okay, let's open it. 5. So I have a mold insert here. Of course, this mold insert is not big, but we're using very small tools here. So naturally, for example, if I want to reach on this edge down here, if I measure this distance from here, it's approximately 52 millimeters. So if I'm using a diameter 3 tool, going down to 53 millimeters is next to impossible because you don't get tools of that length. Even if you'd like to go from the side, it's still pretty deep. Okay, so SolidCAM's tilting or auto tilting functionality allows you to take a three-axis toolpath. It could be roughing, rest roughing, it could be finishing toolpaths, and convert a three-axis toolpath to 5-axis. Simple. So I've got several toolpaths here. Now what I'm going to do is I'm going to pick one of the rest machining toolpaths. I've done the rest machining using a 3-diameter tool, and I'm going to take this toolpath and convert it to 5-axis. So I'll edit, I will add an operation, and I'll say convert 3 to 5-axis. When I'm in the conversion, I'll go into auto tilt, and in the source operation, I pick whatever operations is actually which can be converted. Only those operations that can be converted from 3-axis to 5-axis will be shown here. I would like to use the second operation here, the HSM RM target or the rest machining target. The tool I'm going to use here is not this tool, but I'm going to use another tool that has got a holder attached to it. So this is how I'm going to use the tool. I'm going to use this tool, which has a holder. The tool that was used for generating the toolpath did not have a holder, but this one has a holder. So I'm going to use this tool. Okay, and that's it. I don't have to do anything else. Everything else works as a default mode. There is nothing here. Okay, there is nothing that you need to do. You just need to save. The moment you click on save, the original operation gets suppressed by SolidCAM so that you don't lose your original operation. Your original operation stays as it is, and it generates another operation called as convert the target operation. So I'll just calculate this. This will take approximately about 1.5 minutes to calculate. So let's have a bit of patience. I don't have much of paths. Another after this, just 2 more paths and we are done. Okay. So the first step is loading of the toolpath. So it loads the link if it needs to convert the links. And once that is done, it then starts doing the collision check to see where all the holder is colliding in the toolpath. Now, wherever the holder comes precariously close to the part within a given clearance distance, it tilts the tool. So that's the simple principle that we use in the auto tilt. As I said, it's going to take approximately about 1.5 minutes to calculate this tool path. Okay, calculation is done. We have a tool path here. Now I can take it into machine simulation and I can show it. But the best thing here is let's generate the G code and see this simulation actually in Simco. So I've used the DMU 50 second generation with Siemens 840D for this particular tool path. So you can see that we are generating the motions in vectors and not direct angles. So I'll go to my backplot setup and I'll select the DMU 50 second generation and the controller as Siemens. Say OK. Let's go to the backplot window. The best part here is that you get to see the fixture, the part, and also the tool. Everything is exported from SolidCAM into Simco, and this can be checked for in the simulation. Okay, that's because of the initial zeroing. But we have a problem here, and the problem is that Simco has chosen the wrong holder. This was not the holder that SolidCAM sent. So it's nothing to worry about. I'll go into my tool setup. And in the tool setup, let's look at this tool. So this is the tool I'm working with, or maybe this one, sorry, this one, number 12. I'll edit the assembly. And in the holder, I'm going to choose another holder from the metric holders that I have here. And the holder that I used here was the SR, the shrink fit 4x50. This was the holder. So I'm going to select this, save this, come out. Let's go back again to my first and let's start the simulation. Of course, you can see now I have got wherever it comes precariously close to the area, you can see that it tilts automatically from a simple 3-axis. From a simple 3-axis, it can convert the toolpath to 5-axis. So I'm going to cut down on the speed. So if it's close to the operation, or if it's close to the geometry, the holder tilts or the machine tilts by itself. SolidCAM generates the tilt, the 5-axis tilt. So you can see here straight away, it's tilting, okay? Because this particular portion of the tool is in close contact with the part, so it tilts. So you can actually take any 3-axis tool path and just convert it to 5-axis without breaking a sweat, breaking anything. All you have to do is to define a proper holder and ensure that the similar setup is also on the machine. Okay, so you can actually do both rest roughing, and finishing tool paths. You can convert it using the SolidCAM 5-axis conversion functionality. Right, let's go now into our final 2 parts. So let me open another one. So I'll show you an example here. Go to 5x. Okay, we call it Mexico. And the part is 2, this one. What I would like to show you here is the pattern generation of geodesic. Let's say I want to go parallel to the curve outside here. Okay, so let me show you the curve, not that one, sorry, this one. If I want to go parallel to this outer curve and machine this entire geometry, having a consistent step over, then the option that we need to use here is geodesic. So what geodesic operation looks like? So in geodesic, you can define the geometry both as a model as surfaces. So in our case, now here I've used the entire model as a geometry, no surfaces. So I'm using the mesh data as my geometry. And it must, and here I've done morph between two curves. Because I've used mesh data, I need to specify these two curves. If I'd used surfaces, I don't need to define the curves because the curves will be automatically determined by the geodesic engine or SolidCAM's geodesic engine. So if I look at the curve, my outer curve and my inner curve. So I've got two curves here. So the pattern is going to be morphed between this, but following a constant step over. Okay, and what is a constant step over in this case? 0.5 millimeters, which is going to generate a scallop of 0.01. So how does a toolpath look like? And here, like I said, it won't look from the direction of the tool axis, but it will use its own intelligence to determine a constant step over across the entire surfaces that it's going to machine. So this is how it's going to look like. You can see it doesn't matter where it is machining, the pattern is consistent. The slices have the same passes or the same step over. The maximum step over it is using here is 0.5 millimeter. So it doesn't matter where it is machining, what kind of a surface it is machining, it is always going to give you a uniform cut. So if I zoom in, you can see that it's always going to give you, no matter from which direction you look at, you'll always get a consistent pattern when machining these surfaces. Now, this is the beauty of geodesic machining, is that it can generate the pattern with consistent step over. Of course, all other tool axis controls are available, which are there in generic, are also available. Now, people will ask, what about those people who don't have geodesic? Of course, generic has got geodesic. So if I go to my generic 5-axis engine, where do you find geodesic in your generic 5-axis or 4-axis? You get the generic here. So if I say parallel morph between two curves or parallel to curve, and if I go into toolpath parameters, here my step over calculation approximate is the old method, and if I use exact, I'm using the geodesic engine for calculation. Okay, so geodesic is already inbuilt into my generic 4-axis or 5-axis engine. You don't need anything special apart from that. But for 5-axis, yes, if you're wanting to machine the entire model, then you need the geodesic, because here we don't support the entire model. We support infinite surfaces. Those surfaces will have to be picked by the user. Whereas with geodesic, you have that option of either picking infinite surfaces or picking the entire model as one full solid and allowing it to machine. Right, so that was about geodesic. Let's look at another aspect of generic. So these are all generic, what I'm covering, not even touched any application or automated stuff inside SolidCAM. That I'm leaving it for the third part. I'm going to use, or rather I'm going to go to my folder, webinars. Okay, it's here. Rotary finishing. Like I told you that we have also something called as 4-axis rotary finishing. It's generally used when you have got cylindrical parts, or indeed they need not be even cylindrical. It could be rotating around a cylinder and look like a cylinder. It could have shapes or anything wrapped around them, like jewelry items, electrodes, round electrodes. So you can use any of these parts. So when you get such parts, you can use the rotary finishing. Of course, this is a roller. You can see that we have taken a design and the design has been wrapped around this roller. The roller itself is not a cylinder. It has got a shape here. It's round, but it has also got a shape here. So it's not exactly a cylinder. And what you have in rotary is you can directly pick the model, the target, no surface is business. You pick the geometry as it is, the model, and you machine either along the rotary axis or around the rotary axis. So in this case, it's along, and I've used a pointed tool here. It's like an engraving tool I've used. And this engraving tool, oh, sorry. Yes, please. Run the simulation. So it simply is going to run. It's just going to follow the entire profile and machine and every time it comes to the end, whenever it takes a side step, this side step means this cylinder is rotating by a particular angle, and then it goes again. So this is how it's going to machine. But if you're using a bullnose tool or a ball nose tool and you don't want the tip to cut, we have got an option here within the function. If I open this, in fact, this was done with the bullnose tool. So if I go to the geometry, I can apply a side shift. You can see here, shift from the axis by a particular distance, so that instead of using the exact center, we start using the side of the tool. So this is how it will end up looking like. So if I go to the front view, I'm actually using the side of the tool. It's never the front, but it's using the side of the tool. I'm not using the tip here. I'm using the side. So very important, whenever you would like to machine such parts and use the side, go to, or you can fall back on rotary. So you have got also this option wherein instead of going around along the part, you can go around the part. Okay, stop, and you can see even here, the contact point here is the side of the tool. So here also I've shifted the tool. So any cylindrical parts, mostly the jewelry items, are the candidates, or artistic items. They are the candidates for machining using rotary 4-axis. All right, let's go to the penultimate part in my kitty. So let's open. And this time it's the Contour 5X, which is a pretty simple operation because it doesn't use any surfaces. Like I told you, it's simply using the edge of the part, and all we need to define is certain lines. So I'm going to use a Contour 5X example, simple example. I just have a flowing profile, and I would like to put a chamfer to this edge. Even before we had the chamfering option or the edge breaking option in SolidCAM, we had this option. So what you have here, if I go into the Contour 5X, very simple. So in the geometry, you can see no more surface. It's only the drive curve. So if I show you the drive curve, it's basically the edge. You may have an edge or you may not have an edge, but you just can have a simple curve that's more than enough. Okay, you need not even have a part right there. All you need to have is the curve and the tilt lines. It's more than enough for SolidCAM to generate the part. And then we have the orientation lines, or the lines that are actually going to control my tool axis. So I've just picked the edges of the part here. Again, you can have this, or we could have made a simple sketch. You can use those lines as your orientation lines. The orientation lines here are actually going to control your movement or the tool axis. And the tool I'm using here is a simple chamfer kind of a tool, pointed tool, because I'm going to use this to give a chamfer to it. So let's calculate this tool path. It's pretty quick because there are no surfaces involved. Okay, you can of course give a collision check against certain surface, but that is only if it's needed. Let's go into the simulation, and this is how it would simulate. So it will keep following the curves and it will machine the edge. Simple toolpath. So when we never had edge trimming, when we never had edge breaking, this was one of the methods in which we used to do edge breaking and as well as trimming of parts in for vacuum. This was one of the methods uh, followed by many of our users. So it's a very simple toolpath meant for edge breaking. You can use this particular toolpath. Uh, in the next 5 minutes, I'll just come to one last part because I think I missed it, and we're not going to miss it again. This time it's sorry, I didn't show you the swarf machining, so I'd like to show you swarf. By the way, all these parts are available. Please get in touch. If you're a customer, please get in touch with your reseller. They have the access to download these parts. Of course, they will not be without them. They'll be without the machines that I've shown. It will be having a simple generic 5-axis machine, but you'll have all the toolpaths and other things. And for people who want access to this, most of these parts are also available on our website. You'll have to create your login ID and password, register into it. Go inside and you can find it inside our documentation section. Under applications, you will find all these parts. So what I would like to show you here is I would like to do swarf, or I have got a structural part and I just want to machine this entire side surface using a single pass. So I would like to, and the best possible way to do it is using swarf. So let me create a swarf operation. Again, swarf is part of our generic bundle. So anybody who is the generic 5-axis or 4-axis will have swarf machining also. In the geometry, very simple. I just need to define the swarf surfaces. So I will pick these surfaces here. There are small bits of surface. Again, there's another small bit here. Let's pick the surfaces. Okay, it's done. And then it needs to define the flow surface. The flow surface is an optional surface. If you want to make sure that the tool does not collide against the bottom, it's always a great idea to pick the floor surface. The floor surface is this surface and also your fillets that are there, because you're not going to machine the fillet using your swarf. You're going to be just touching the fillets using the swarf engine or swarf machining. You're actually not going to be machining it per se. So that is why these surfaces form my floor surfaces. The tool I'm going to use here, let's see what are the tools that we have. I'd like to use a taper ball nose. Yeah, I'm going to use a 12 taper ball nose with a pretty long cutting length. Okay, and let's go to the levels. Nothing, everything is automatic. Only the machining side here, instead of using auto detect, I will say detect the normals based on the surface normals and machining side, because I just selected the surface. This surface can be machined from this side and also from the other side. So the surface normal will decide which side I would like to machine this part from. That's it. Only thing is I like to provide a lead in and a lead out, and I hit the calculate button. No tool access business, nothing. Simple calculation. Just select the surface and you're done. So I have got the toolpath here. And if I run the simulation in my host CAD, this is how it would look like. Because this is straight, this is simple, you can see. Now this side is tilted, so it starts tilting. But you can see that I have got another surface here that's tilted here. Now Swarf is pretty smart. It's having a tilt, and as it approaches this surface here, you can see that it starts doing another tilt, so that it's anticipating the surface. Right? It's anticipating the surface here, so it creates that tilt in both. Now this particular point here has both. It has got the tilt as well as the lag angle here. Okay, so It will machine this entire surface in one pass. Now assume that you had a small cutting length and not as the entire surface, and it was not possible for you to machine this in one go. So Swarf allows you to also machine this particular surface using multiple passes. Okay, not just one pass, but you can say, I would like to have by number of slices, I'll say 5. I would like to have 5 passes. And the option is I can step or I can go parallel from bottom, I can go parallel from top, or I could morph from top to bottom, because here you can see the top area is having a different shape and the bottom area is simply flat. So here I will create a morph. Levels, I don't need automatic. I just want to go to 15, and the safety distance is 10 and 10. I'll hit the calculate button. So we are going to have 5 passes, but they are going to follow the shape of the upper surface. And let's change the color so that it's more visible to you. I'm going to go into the toolkit, which is the tool number. This is T3. So I'll go to T3, change color to blue. So how my toolpath looks like, you can see that it has morphed itself. The upper first pass is following exactly the upper edge, but the tilt and all is happening according to the surface. And the last pass is following the floor. And passes in between are basically morphed between the upper pattern and the lower pattern. Okay, so Swarf is a very powerful function and a very easy toolpath to generate, because it doesn't have any definitions that require a lot of work, nothing. You just pick the surface, pick the bottom surface, and you have the toolpath. Of course, there are collision checks available. Like the generic, all the collision checks are available inside the Swarf. Okay, so I believe we have completely covered our generic 4 and 5 axis toolpath. It has got everything. We saw quite a lot of paths, different ways of machining. We also saw some other aspects of our generic 5 axis like drilling. We saw conversion. We also saw today quite in depth the circle end mills and of course swarfing. So we have covered our entire package of generic 5 axis. So if somebody buys the standard package of 5 axis, this is what all he will get along with the standard 5 axis. In our part 3, which is again going to happen, but it's going to happen on 12th of August, that's a Thursday, we are going to look at the automated functions. Today, we have defined, for example, machining an impeller we have done with so many definitions. How about doing it with few clicks without having to define any of those things that we defined while machining our impeller? So all these automated operations like rotary, multi-axis machining, multi-bait, port, edge breaking, and edge trimming, we are going to see in our part 3 on 12th. And I will see you again next week. Till then, thank you very much for your patient listening. This webinar is recorded and it'll be available to you as a part of the email that goes off within 24 hours of the session ending. You will get the YouTube link on which you can see this session again. It is recorded. Like I said, the parts are already available with your resellers. If you're a customer, it's available with your resellers. Get in touch with them, or you could even download it by registering on the SolidCAM website. Thank you once again, and have a nice day. Take care. Bye-bye.